Well, good afternoon, everybody. Hi. We're going to get started in about 30 seconds. Can everybody hear me okay? It's kind of a dumb question. Who can't hear me? Raise your hands. Who's been here all day? Who wishes this could only be 5 minutes long?
Give it to him.
Yeah, well, give me 5 minutes. We'll see if you stay. Okay, I'm terrible about moving around. I must be partially Italian because I'm always doing this, but I'll try to stay in one spot. Can everybody see the screen okay? All right. So good afternoon, folks. My name is Darren Tilman. I am the president of Power Flow Systems, and today we're going to talk about exhaust systems. So before we get started, I'm very curious. How many of you are A&P/IAs? How many are here not as A&Ps or IAs, but as pilots really interested in learning more stuff? Cool. And how many of you didn't know why you're here? Okay, well, you're getting up there in age, I understand. Has anybody seen this presentation 2 years ago? Did you remember all of it? You want to come up and do it? No? All right. My jokes did not improve. I apologize in advance. They're just going to get worse. All right, a little about me and the company. So Power Flow Systems is from Florida. This is my cold, wintry weather for us. So we came up here to experience winter. And I realize you guys, someone just said it's half summer already for you guys. So, you know, it's all relative. So if you see me like start shivering, I'll put on my jacket. It's the way it's going to work out. So Power Flow, we're in Daytona Beach, Florida. I am an A&P. I got my associate's degree from Embry-Riddle in aircraft maintenance technology, and I got a bachelor's degree from Embry-Riddle in aviation technology, and I got my chapter 11 from Embry-Riddle, courtesy of the Bills. I kid, you know, it was expensive when I went like 30 years ago, but today it's literally about 10 times more expensive. So it's a very serious, you know, doctors come out cheaper, I think, so. Yeah, small company. We're not as small as we used to be. We're gotten pretty big now, but technically I am also hold the titles of engineering manager, QC manager. I'm also a DAR. The point of that's supposed to be that I do know some things, maybe. All right, well, who are we? We're the leading designer and manufacturer of tuned exhaust systems for General Aviation Aircraft. We started in the early 80s messing around with things. We didn't get really serious until the late 90s. Got our first product certified in 1999. That's on the Cessna 172. And then we made a monster and kept going. We now are on 17 major aircraft, 4- and 6-cylinder aircraft engines. We are also available on some experimentals, but it's only experimentals that have the real estate to put the kind of tuned systems in that we do. We got about 7,100 of them flying right now. I'm confident there will be some with Power Flows coming in here tomorrow. We are the OEM exhaust system for the Diamond DA40 and their short-lived twin with had Lycomings. Not because of us, it's because they had to swap engines. And we also, how many of you ever heard of leading edge exhausts? Show of hands. Awesome. Great company. Unfortunately, the founder and owner of that company, Dane, passed away unexpectedly. And we heard about that and said, gosh, this is too good of a product to let it go. There's too many of you guys that may be seeing it or operating on it. We didn't want it to die. So we came along, and in the end, we were the only brave/stupid people that said, hey, we can make that go. And so here we are. We purchased them in 1999. They have an exhaust system for Cessna 180s all the way up through 210s, and then the Super Cubs. And it's a really, really cool product. So we took it, moved the company from Alaska all the way down to Daytona Beach, Florida, because we thought that would be fun. It's also where we are. And we had to learn how to essentially reverse engineer the product and then apply our own technology and engineering to improve on some little minor areas and to get it into serial production. We're not quite fully done with that. We're almost at the end point. We've got everything back in full production except the Super Cubs, and that's starting right now. Oh, look, I just said all that. We've got shipped over 320 Cessna 180 through 185 exhaust systems as of like last week. So we really got them up and running now. The Piper Cubs and stuff, that literally, we have the first test cases that are out of house, shipping out over the next month. And those guys are going to confirm what we've done is working well, so we can then release them. So as an exhaust design and manufacturing company, we have the benefit of looking back at the last 100 years of exhaust designs and saying, what really worked well and gives good longevity and good maintenance operationally. And then we also say, hey, what doesn't work? Tried to take the good ideas, get rid of the bad. In some cases, there is only one way to skin the cat, but there's a lot of other areas that there can be improvements, and we did strive to do that. Okay, the 4 forces of flight. How many of you have this shirt? I mean, like, you can't be a pilot or mechanic without it, right? Now, I'm going to equally put down pilots and mechanics. I'm both, so I think it's fair game, right? So, we all view anyone from the FAA here, before I make this joke? Anyone going to admit to that? There is a guy from the FAA back there. Okay, plug your ears. Are you here to help us? Always here to help us, that's good. So, there's the FAA, right? That's a force on the aircraft. They don't teach that in pilot school, but it turns out that's the drag, right? Well, so pilots view mechanics as they're the drag. It's those darn mechanics always like finding things wrong with the plane. Just let it go. Those stupid inspections, we don't like those things. They cost money. I had a really good A&P teacher, a good old boy from Georgia, who said, the mechanic's job is to separate the pilot from his wallet. Now, I didn't really feel that was a great way to put that, but you know, we're all trying to do the right thing. You want that airplane to fly. You want if you're going to be in it, that guy's family is going to be in it. You could be in it. You want to make sure there's no problems, right? So it's not really as adversarial as some people view it. We're going to talk about 4-stroke engines, okay? What I'm going to talk about is in broad terms, because this is meant to be educational. You can apply some of the stuff I'm saying to larger displacement, smaller displacement, even 2 strokes. But it really varies quite off the path, so I'm just warning you. I'm going to talk about 4 strokes. We have a lot of expertise in both continental and Lycoming at 320 and above. All right, what's a detailed inspection? Anyone want to give me a sound bite? What would you call a detailed inspection on an aircraft? Well, an annual, okay. So, should an annual be, hey, it flew in, it should be able to fly out? Probably not, right? So the FAA, for good reason, says, hey, you need to have a detailed inspection on an annual. That's opening up your panels, that's checking the oil, it's checking your timing, it's doing all these things on the airplanes, things that probably have not been looked at in depth, at least for that prior year. Well, they also require a detailed inspection on the exhaust. Unfortunately, and none of you don't have to admit it if this is you, what a lot of people do when I've seen in the field, where the detailed inspection on the exhaust system involves, hey, if I grab the tailpipe, did it wiggle? It didn't, we're good. Or, let's just use the CO sniffer to check to see if there's any leaks. Now that's a legitimate method of seeing, hey, is there any cabin heat violations, i.e. the exhaust is cracking and we're putting exhaust into the cabin heat area. But that's not the whole thing. It shouldn't be the whole thing. It definitely is not the right thing. So much, my perspective, so much more should be done to the exhaust system. And that's a detailed inspection. So if the detailed inspection on the aircraft is, hey, let's open up things and take it apart and look, the same answer should apply to the exhaust, okay? And let's face it, on a normally aspirated engine, most exhaust systems aren't really that hard to take apart. And in a lot of cases, the exhaust systems have things built into them that are supposed to be maintained and disassembled routinely. And if they're not, The built-in failure mode now occurs where the thing that's supposed to move can't. So guess what? It now stresses things out. Why does it matter? Okay? FAA has put out a whole thing and a whole study where they said, hey, the top reason for carbon monoxide poisoning is the muffler systems. Well, I mean, that makes sense. You're not getting CO from anything else. In 92% of the cases, the muffler had more than 1,000 hours in time and service. So mufflers are generally where we get our heat from in normally aspirated aircraft. Why? We don't have a liquid-cooled engine usually. Yes, technically there's oil, but we don't use the oil radiator, so we're running air over that manifold. We want that air to be free of exhaust gas and issues. So over time, exhaust systems, and I'm going to give you a giveaway here, exhaust systems corrode from the inside out and the outside in. Okay? And if it's corroding, what it's literally doing is it's removing material over time. So what may start out at 35 thousandths or 49 thousandths in thickness, 1,000 hours from now, it is not going to be that thick. It will be thinner. And things will, over time, due to the combination of just operational and also stresses from vibration, etc., it's going to create a problem, and eventually something's going to give. That's the crack we're all worried about. It is one of the few single points of failure that can incapacitate a pilot and bring down the aircraft. Has anyone ever had CO in their cabin before that they noticed? You have? Yeah? How'd you notice it?
We were getting kind of dizzy, and then the thing started turning black.
The little, the dot of death? Yes, okay. So you were getting a little dizzy. So
it was a known issue, though.
It was a known issue. You're a brave pilot. You said, I know that. We're just going to go.
We thought we fixed it, and we went up and it.
That's fair. It wasn't fixed. Okay. You know, a CO is not something to mess around with. Yes, you had your early warning signs. You eventually saw the black dot. You noticed it. You were aware of it. That's good for you. You didn't continue the flight and say, well, I'll just breathe less. I mean, because ultimately you were going to breathe less, as it turns out. Spoiler. So you want to be aware of that. There are lots of tools out there for us pilots and operators that really should be taken advantage of. You've got, you know, CO detectors you can put in the cabin. Heck, you can go down to Home Depot or wherever and buy even a household one. They're not great, but they're better than the black dot's very passive. If you're not paying attention to it, you're not going to see it. And by the time it's turned black, it's probably not so good. But we want to do that. Lightspeed has a headset. It's got a built-in CO detector. It's a pretty aggressive detector because it'll pick up gases that have circulated into the cabin just from weird airflow if you've got the windows open. But I'd rather have that as a warning than be like, I feel kind of faint and go to sleep. So we always want to be aware of that. Our job as mechanics is let's make sure that we are really keeping it as safe an environment for the pilots as possible. Some countries require aggressive testing, i.e. pressure testing of the cabin heat. Oh, I gave it away. It's Canada. The US does not require that. Why? Is Canadian air different? It's colder? Well, it's apologetic too, but it doesn't make sense not to be testing it, to pressure test that. I don't know why it's not ever really come down past the border, but as a technician, I will pressure test things. It's not required, but I'm not going to be the one signing it off and saying, well, I could have looked at it and I didn't. All right, stress and vibration, okay? What causes stress in aviation besides the FAA? Okay, well, all right. You're flying something, most of us are flying things with propellers and engines. It's a giant vibrating object, series of objects to be fair, right? And vibration is a stress, okay? So if you have something that's vibrating a lot, you're adding stress. You've got an exhaust system that's attached to an engine that's got 4 or 6 cylinders, piston flying around, okay? And they are creating different harmonics and different resonances. Ultimately, things add up. So what do you want to do? You want to avoid that, or more correctly, diminish it. Oh, look, there it is, exhaust corrode from the inside out. Let's talk about some traditional exhaust problems. This is a traditional exhaust found on a lot of Cessna products. You can see there's a beaded clamp, and this is the riser. This is upside down, to be fair, okay? So the cylinders are here. There's the risers. There's the beaded clamp. So that's an okay thing, but what happens is your engine is nothing more than an air pump, and it's pumping air through. And so the ultimate effect of that, I'm going to exaggerate the motions, is this cylinder moves, and ultimately everything over here pumps in. So you get a little movement over here, then back here, and then back here. So what's happening is those risers and that central muffler assembly is getting pumped and pushed, and it wants to move. Eventually, it will make room. You can't see it because of the way this is presenting, but there's some yellow streaking going on. That yellow streaking is exhaust starting to leak out, and it's from that movement. The failure mode on this is not something that happens in 100 hours. This is like 1,000, 2,000 hours typically, where those beads start to wear out. And the answer is, it's a part that's going to need to be replaced. Another place to look. Here's a good thing to know. Anywhere something's been welded is an area where there is going to be a potential for stress. Typically, it's not on the weld, it's around the weld. It's called the heat affected zone. These mufflers have these stamped flanges, and there's a big old beefy weld going around that. Okay? So typically, you will see cracks in this area or that area. Why? Because your engine's that big air pump. It's pushing a lot of air in, and then it's getting it directed from both sides, and some of it's ultimately fighting the other ones, and some of it's coming out. So basically, your muffler's kind of doing this many times per minute. Okay? That's very exaggerated, but that's what's happening. So you always want to look wherever there's a weld. You always want to look around for a crack. Over here, that's supposed to be carburetor heat, supposed to keep out nuts, bolts, and small children. I would argue it's not very effective. Anyone want to buy that one? Yeah, see, it's missing parts of it. So that's an issue when you should be looking at it. So what I always tell pilots that want to learn stuff, I say, look, get to know how it's supposed to look correctly, so you have a baseline for comparing to when it's not correct. When there's mesh involved, I tell them, just touch it lightly. If it moves, it's not supposed to move. That's a problem. Over here, this style exhaust system is commonly, it's called a Naleno style exhaust. Instead of having the two pipes going into the muffler, they Y together and then they go in. Similar things are found on, say, 6-cylinder Cessnas, where the risers kind of look like a W, and they kind of all form together, and then they go in. So this one's fun. Do you see the patch? So apparently it was okay to patch. Well, the fun part was that's a patch on a patch. How many patches are allowed, mechanics, on a muffler, do you think? As many as you can get on. That's an honest answer. It's functional. I don't know. Now, why is it cracking there? It's cracking because those cylinders, each one is trying to move and expand and contract slightly differently. It has a natural tendency to want to have the ability to move. But when we've made them go together, there's no movement allowed. So the crack was the stress relief. It made its own movement. And then the mechanic came along and put a patch on it. And then, darn it, didn't it happen just a little while later? Another patch. And then as many as you could fit on, right? So why is that? Intrinsically, it wants to have movement. It wasn't allowed to get it. It made its own. This is another example of when something wants to move and can't. This is where these two, this is a Y pipe, goes in here. Okay? And spoiler, you're about to see there's a big crack here. Apparently there we are. Why did it crack there? Because it wanted to move and it couldn't. And now, remember I said, look adjacent to the weld? Here's the weld, there's the crack. Now, it's possible the weld may have contributed to the weakening of that area. In fact, that's very likely. Or it's also the inherent design of that pipe. It wanted to move and it couldn't, so it relieved itself. All right. Let's pick on a Mooney's. Yeah, any of you have any Mooney's flying around up here? They're not a very Alaskan kind of airplane, are they? It's probably to do with that 3-inch of prop to nose ground clearance. Anyway, so on a Mooney, underneath that heat shroud is this. Now, there's some ridges in there. Any idea why there's ridges?
Heat exchange.
Heat exchange, nice. Anything else? Strength. Anything else? Expansion, possibly. So all of those are really good answers, and in my opinion, they're all correct. The way that those ridges are put in there, that's metal that was flat and has been stressed to make a ridge. Where do you think the crack's coming? Where that stress was, that ridge was made. But on a Mooney design, this is the same source of cabin heat and carburetor heat. You have them both. That is not allowed in today's certification standards, and the reason being, if you have a true backfire and you had your cabin heat on, and you had your carburetor heat on, you've just created a gas pathway to come in through the cabin heat. 4 out of 5 pilots would agree that's not good. You guys are good at math, right? What happened to the 5th one? Right? I told you, my jokes don't get better. All right, Cardinal RG. Anyone ever seen one of those flying around? Anyone know who Rube Goldberg was? Okay, I think he designed it. He's probably designed a lot of things, you know. Here's the Rube Goldberg special. Here's the risers on the pilot side. They're coming into this can, and then they have to jump all the way over to cross over into this can, which is joined up with here, and then over there. This is from an airplane that came into our facility. There's those lovely beaded clamps. I'm moving too much there. Lovely beaded clamps. You can see all of this contraption. Now, anyone that's ever worked on a Cardinal RG will tell you the exhaust is terrible. It's terrible because there's so many points of failure in here. This particular airplane had come into us after having been worked on at a Cessna service center who'd given it a clean bill of health. They apparently felt there's no such thing as too much safety wire to hold things on. So he came in, he wanted to get an exhaust system. We said, that's fine. And he said, well, gosh, this seems kind of close to that nose truss. That's probably important. 4 out of 5 pilots would agree the nose gear should work. And what happened was, once we removed the exhaust system, that's what we discovered. Okay, smart mechanics out there, how much of that is okay? Would we agree that it's not okay? Yeah. Now, had this exhaust system ever been removed during that annual, guess what they would have seen? They would have probably figured out that that's starting to make contact. But did they? No. They felt safety wire was the appropriate thing. So the Cessna Cardinal has, I believe it's 3 different service bulletins. Each time they added a new layer of structure to help support the weirdness of this exhaust. And these guys had just, at some point, the mount had broken, and that's where some safety wire came in, because, you know, that fixes everything. And this whole thing started sagging down against the truss, thereby creating a new problem. So that's caused by that crossover tube. How much metal can be eroded from an engine mount? Anyone want to shout out an answer? Yes, or taken away. No, the FAA guy is going to plug his ears. You're okay, go ahead, speak. Okay, so roughly speaking, usually if all else fails, they would default to AC 4313, and it's 10% of the wall thickness. I'm pretty sure that's more than 10%. I think we could agree. So it's bad. Did this happen overnight? No. Again, I'm giving you real-world examples why exhaust systems need to come off the airplanes periodically for a detailed inspection. because you sure weren't doing a detailed inspection on that truss with the thing in the way. There it is. Okay. Ball joints. We love ball joints. Ball joints are great. They give you the ability to have things move. But a ball joint has to be maintained. When I say maintained, it should not be frozen up. If it's frozen up, it is no longer working as a ball joint. You might as well have welded it. So this is commonly found on, again, things you don't find up a lot up here at Moody's. A lot of Cessna twins use ball joints, okay? Not if they're turboed necessarily, but the normally aspirated ones will use ball joints. Same thing. They should come apart periodically. Now, what do you do about them? High temp anti-seize is a good answer. That'll free it up. If the hardware looks corroded, it's probably bad to leave there. Maybe take it off, replace it. Okay, inside most mufflers are these things called flame tubes, cones, attenuators. Their whole purpose in life is the gases coming into them then have to diffuse through it. Through some miracles of physics, that's a gas exchange and it slows it down and ultimately it makes it quieter. A little quieter. And those are okay as long as they're intact. So, another thing I encourage a lot of people is to get used to looking up their tailpipes. Okay, now with today's day and age with borescopes, etc., you can put something right up there. You don't even have to get too creative with a flashlight, especially if there's angles involved. But look up there, get to know it. Most exhaust systems are certified with flame tubes in them. The key problem with that is if the flame tube is there, it will eventually deteriorate. It will eventually break up. You hope as a pilot that it breaks up and leaves the aircraft without plugging up the hole. Now I said that your aircraft is your engine is an air pump. So when it's pumping along, if that exit output is blocked, what do you think is going to happen? Yeah, well, we got a very technical answer. Pressurize the crankcase, yes. Also pressurize your underwear. What's going to happen is the air pump's going to make a new hole. New problem is we don't know where the hole's going to be. You hope it's not something that's, important, like an oil line or a gas line. So this is really important. Looking up the tailpipe, looking to see how intact that is. Old mechanic trick, you take like an old wooden dowel or a broomstick, you push it up. You reach it, you make contact. Push lightly. If it comes up and then goes clunk, clunk, it's not good. Time to replace that. Oh, look, here's some examples where things were not going well. This guy got lucky because the flame tubes blew out and it did not make a new hole. Now, technically not airworthy any longer, but also probably a little louder. Some of these exhaust systems, these flame tubes are actually kind of structural. And when you take away the inner support of a structure, it's not good. So you also want to keep that in mind. Here's some more good, bad, ugly pictures here. Ooh, this one's a fun one. Anyone recognize, well, yeah, sure you do. This is an exhaust system on a Cub, a PA-28. They've been using this style since the 30s. Okay? Very interestingly, it had some good elements to it. But right down there at the bottom are two slip joints, which are never ever maintained by most people. So your engine is trying to expand and contract, cylinders are trying to move, we don't let them. So these things get stuck, so then they stress out the flanges, or they stress this out. Gases come all the way into the back here, they fight through this muffler, which has a recurring 100-hour AD, we're all familiar with that if you're an IA or an A&P. And that AD is because, well, this thing kills people when it cracks. We don't want it to kill people, so we have to keep checking it. And inside of that, that's where your cabin heat's coming from. This is a carb heat shroud. That one also lives up to your point about you just patch it as many times as you need to. It's common to find 3 to 5 patches or crack repairs on this. I mean, it's okay, it's what you need to do. That's a stupidly expensive assembly. That's at almost $2,000 last time I checked. It's not a $2,000 part, it's just the way it is. So we had another Cherokee, we had a Cherokee come in, and the pilot says, oh yeah, I had a little backfire when I did the mag check. So, well, can you describe backfire? And he's like, well, it went boom. And I said, okay, thank you. I said, did you maybe turn it off? He goes, yeah. I said, did you turn it back on? He goes, yeah. I said, okay. So he said, it's okay now, it flew over. I said, that's referring to my last thing. If it flew in, it can fly out. That's not always the right answer. So then we took a little closer look and we said, this is looking a little weird. Let's look a little closer. Oh, how come I see daylight through your air filter? That's, by the way, not a feature. That's normal. I don't think the filter's filtering very well when it's got that going on. And he goes, well, I don't know. And then I looked up here and I said, I see shrapnel. Did you take flak? You know? And the real answer was, yeah, that's a zoomed in thing. So this guy had overpressurized his exhaust when he turned off the engine and turned it back on. And the miracle of science with the combustion, it went boom, and it blew out the weakest point. Remember I said it makes a new hole? There it is. Unfortunately, that hole was also facing his air filter. When we took it off, this is what we found. And we said, well, no bueno. This was what the end of his muffler, that's the feeding in point from the risers at the back. This is his muffler. Do you think this guy's had a good annual recently? Maybe ever? Right? Congratulations, you found where the tube was welded and you took it apart. Okay, not good. Inexcusable to me. Why is this, whoever he was going to get his inspections, not doing anyone any favors. All right. Yeah, okay, well, I already said that. All right, so what's the purpose of an exhaust? Get the gases out of the engine and away from the cockpit and the aircraft, right? We need a heat source for the cabin. You need one for a carburetor. We'd also like to reduce the noise. There is for certified airplanes, there is a noise standard. You must have a certain decibel level. It's a convoluted test. Okay, it's also very fatiguing. Anyone fly, do they fly RVs up in Alaska? Yeah? Yeah, okay. RVs are usually really loud, right? Because they have no mufflers. So they're really fatiguing. So the solution to that is you buy good A&R headsets. Okay, well, that's one way to do it, right? It's like driving an open pipe Harley across the country. You're going to be more tired than if it was a quieter muffler. Why? Noise energy is noise energy. And your body has to fight it. So, let's talk about an exhaust system design, elementally. If you didn't care about any of those things I just talked about, cabin heat, sources, noise, nothing, well, there you go, you've got it. That's a P40, I think it is, but it's also found on the P51. It's just open stacks. Okay, loud as all get out, but we don't care. You heard that coming, it wasn't usually the issue. But you're not going to have any benefits from it. It's not going to hurt the engine, but it's not going to help the engine. Here's an RV, this is a typical RV, it's a Vetterman exhaust system. So on a Lycoming engine, the firing order, strangely, is right side front, right side rear, left side front, left side rear. 1, 3, 2, 4. I don't know why they did that, that's the way they do it. So here, the gases come out of this cylinder, come all the way across. They get picked up, they join with the gases from here, and they go out. There is no muffler in there. The same is true on the back side, okay? Very, very cost-effective exhaust system to build. Doesn't have a lot of area for cabin heat, doesn't have any muffler, but it works. And it works really well because in the sense he didn't tie the cylinders together that were going to fight each other. The worst cylinders exhaust design you can have is the ones that fire right next to each other and they join together. 1 and 3 should not be tied together. It's a bad idea because they're literally, the gases from the 1 are going to fight with the number 3. This guy doesn't do that. That's a crossover system. It's called crossover because it's crossing over the engine. Or really, it's crossing under the engine. All right, so another thing about elemental exhaust design. This is typically found on Cessnas, say 172s, 152s. That's an Eleno style exhaust. That's found on a lot of things, Grummins in particular. Now, they both start out life, they started at something like 105 to 125 horsepower. And the simple answer in aircraft design and manufacturing is, if it's working already, leave it alone. So that's what they did. They literally just kept everything the same, and if the engine got wider, they just added a little length to the risers. That's all they did. So if this thing was designed originally for 125 horsepower with a 3-inch output, if you make that 150 horsepower, can we all agree empirically it's probably a little more resistance? Well, what if we make it 180 horsepower? It's even more resistance. Well, this same thing is a 3-inch pipe. That's either 2 1/4 or 2 1/2, depending on the version we're looking at. This is also used on 180 horse. So just without knowing anything about any kind of design, the guy with the bigger hole is going to be less restrictive. So this Cessna exhaust fits in larger cowlings. Grummins have smaller cowlings, so they have to go with smaller everything else. Not great from a design standpoint, but it's a functional standpoint. Oh, look, I gave all that away. Cherokees, they started out 65 horsepower Cubs, used it all the way through 180 horse. Right? Doesn't make a lot of sense, but it was good enough. Now, the aircraft manufacturers didn't have many choices. We weren't around, and even if we are around, there's a competitive issue. If you didn't like your Cessna 172, sir, step into the 182. 182 is not enough power, step into the 185. That's just regular salesmanship. Let's just sell you into the next bigger thing. They're disincentivized for making the 172 operate closer to a 182. They would sell fewer 182s, all things being equal. The same thing with Pipers, etc. So they were never incentivized to do it, right? It didn't make sense for them. All right, so this has a 2-inch output. So 180 horse has to come out of a 2-inch pipe. Not so good. All right, so how does the tuned exhaust system work? The whole concept of tuning is not new. NASCAR and all the racers have been figured this out in the 50s and 60s. It's let's make the headers for your plane or for your car, let's make them so your engine breathes. Now let's define what is breathing. Once we get past let's get the cylinder empty as much as possible so you can get as much new fuel air in there as possible. That's its whole concept. How do you do it? Well, it's the source of the force, right? 4-cycle engine. Intake, compression, power, and exhaust. So if you have a traditional exhaust system, let's picture this. You guys just turned into a combustion chamber, okay? There's your intake, there's your exhaust port. So we filled this area just from a standpoint of, we got to start somewhere. Boom, you're all in here, you're all fuel-air mixture, you're in the right ratio, you're ready to have a good time. You're going to explode, okay? And then we compress you, we spark you, boom, you've exploded. And then I open up the exhaust side, and instead of opening it up and allowing you to just escape gracefully, I've actually met you with the force from the other cylinders. Some of those gases are holding you back. So now I've got a 60-mile-an-hour wind pushing in while you're trying to go out. So by some miracle, eventually, most of you get out, around 70 to 80%. We open up that, and now you're trying to go this way, they're trying to come in, but that pressure is going the wrong way, it's a suction. So now you don't know where to go. So as a result, some of you stay in. And now you've been burned, you've all exploded, so what you are is your residual heat. We see it as cylinder head temperature. But you're also occupying space, so not only are you hot, you're also taking up some of my space. So now, my cylinder volume is reduced by somewhere in the region of 20 to 30%. And I'm stuck, because the cycle of life is going to continue, the cycle of that engine. That door is going to shut, that door is going to feed in some fresh air mixture, and we're going to cycle and repeat. The idea of tuning is, let's not do that. Let's not let those gases from the other cylinders fight with you. Let's actually harness and make a suction. So the idea of a tuning is it's made up of three elements: a primary tube, a collector, which is literally by definition where the tubes come together, and a secondary. They're designed to be, the primary and secondary are designed to be a certain length, diameter, thickness material. If the cylinders are capable of equal power output, then the primary tube should also be equal. That makes empirical sense to most of us, which is, well, why would you want one tube to be 12 inches and one to be 35 inches? Right? There's going to be things going wrong there. So let's make them all the right number. And then it has to be the right number to create the pressure pulsing that we want to do. And as a result of that, you can essentially tune the exhaust system so that it is going to be the most responsive or the most suction at a given resonance or a given RPM. We see it as RPM as operators. So, how does it work? I'm going to show you a slide, and I'm going to have to go reasonably fast through it, so just bear with me. So, the way you can get stuff in and out of this room is when both doors are open. That's overlap. Overlap is when the intake and the exhaust valve are both open. So that's when we can push or pull air around. Okay, otherwise it's a one-sided battle. So what we're going to do, and this is the thing I'm going to fly through in a second. I'm going to zoom up real fast. Here it is. So this is actual instrumentation on a Cessna engine. We knew it. We knew the exhaust system worked, but we wanted a map. What's going on? What's the pressures? That black line represents 0. That's above it is a positive pressure, below it is a negative. This was the same engine, same day, 2 hours difference. And it was the same RPM. So all we did was map what it did with the stock exhaust and then mapped what it did with the tuned exhaust, because we wanted to illustrate and see what was happening. So follow me with this. The blue line was the stock exhaust. So when the exhaust valve opened after combustion, the peak pressure came up, went to 15 inches of mercury, and as the engine continued to cycle through, the peak pressure came down, and then it became kind of a suction. And then when the intake valve opens, that door opens, the exhaust went positive. Well, if I'm trying to get you out the door, how are you going to get out the door if there's a breeze pushing you back in? There it is, there's that breeze. Meanwhile, the intake is kind of a suction. So you actually are incentivized to go that way, not that way. So you're not going to want to leave your cozy little chamber. So eventually the exhaust valve finally closes, the intake's more of a positive pressure, and then the cycle goes on. The tuned exhaust system comes along, there's the same spark point. The peak pressure is actually a little more than twice as high. And then here's the cool part. It then takes a big dive towards suction, and now it's sucking. And right here, your door, instead of a 60-mile-an-hour breeze, is a 30-mile-an-hour suction. Meanwhile, the intake, once that's opened, it is still negative, but it is less negative than the exhaust, so essentially it's more of a positive. So you're being sucked out that way and pushed in from this way. Guess where you're going to go? You're leaving the building, folks. You're going out the door. So then that suction gets really strong about halfway through that overlap, and then eventually comes up. The whole time your intake pressure is going up. So the end result is this room that was only getting 70 to 80% emptied is now getting somewhere around 97 to 98% emptied. So your cylinder heads are suddenly less hot. Why? You've left the building. We took the exhaust out of the aluminum and put it in the stainless. That's good. So that's emptied. You're here now. There's more of you in here that are ready to make power. So we just improved the ability for that cylinder to create power. That's the net effect of a tuned system, is it makes more power. It's an efficiency change. It's technically a volumetric efficiency change to the engine. Why? We've emptied the cylinder. That's a close end, and I'm going to let that come through here. And if you want to take pictures of that, you can. So the key point is, let's get the engine to work for itself instead of fighting itself. And what can you do with that efficiency? You can do a lot of things. So how do we do it? Well, it's about length and diameter. So picture this. This is where it bolts up to your engine. The gases have to come all the way through this isolated tube. They don't join up with its buddies until right here. This one has a relatively short tube here and a relatively long, this is called a collector tube. Okay? This has a really long version of this and a relatively short one. If you take a piece of string and go all the way around to here, and then all the way around to here, you're going to get the same number within a very small number of tolerance. That number, by the way, for this particular setup is around 40 inches. So 40 inches, 3.5 feet of tubing before those gases can possibly interfere with each other. And the truth of the matter is they can't interfere because it's a supercharged high pressure. So you make a big exhaust pressure in here, and then there's a pause. What do you think comes after a high pressure? A low pressure. It's the timing of the tuning is to make that low pressure be when your valve opens next. That's all tuning is, it's timing it. It took me a long time, I'm very slow. I have the most perfect job when to prepare for this. I played the trombone for 12 years. That is, by definition, a tuned exhaust. It took me like 15 years to figure out, wait a minute, I was prepared for this job the whole time. That's all that is. You want to change the resonance. Now, we don't have to change the resonance in an aircraft because we operate in a very small, limited RPM band. Most airplanes operate between 2,200 and 2,500 in most of their time. Yes, we can take off constant speed people around 2,700, but you don't cruise there. You tend to back off down into the 22 to 25 range. Fixed pitch people can't get to 2,700 on takeoff. They're around 2,450. That's where we tuned it for, 2,450. Why? We wanted to give it the biggest results on takeoff and climb. It's also an important thing because if I wanted to, I could make the exhaust system produce more power through that harnessing and emptying thing we were just talking about than the engine was rated for. Technically up to 7% more. But then I have a new problem. How do we say about your 160 horse engine that's on a certified for 160, that's on an airframe certified for 160, and I just made 172? Those people with the initials that start with F and end with A would have a real issue with that. We don't want to do that. So we've essentially targeted the RPM band to not only be the most useful, but also to be careful to not go over the rated horsepowers. On a fixed pitch airplane, 2,700 is where the top horsepower is. Just don't go over 2,700, we don't have a problem. Constant speed, the airplane takes a bigger bite out of the air, so its torque, it just takes that and slows down the engine. It's not tuned for 27, it's tuned for 2,450 or 2,500, depending on what we're talking about. What do we do after this? That's called the collector. Then there's another tube. That tube is where we put our sound chamber. And the way we do it on our, we call it our legacy products, is it's a non-obstructive muffler. It's literally a round tube. You can see right through it. Looks like this. It's that with some wrapping on it. A lot of people say, oh, it's a glass pack. Well, okay, sure, it's a high-tech glass pack, but it's a glass, it's not made, there's no fiberglass in there. What's in there is stainless steel and basalt fiber, and that wrapping will eventually dissipate over time. But the clever thing is, this is certified even with that wrapping gone. It just gets a little louder and you lose 1.5 horsepower of the gain you had because we've changed that dynamic. And it's designed to be replaceable. So you don't have to go send this thing out. You just pull out these 4 screws, put a new one in. Oh no. How do we do it? That's what it looks like in a Cessna 172 type exhaust. Now, remember I talked about how your engine wants to move, okay? We are fanatical about this. We designed in, there's no clamps holding this here. These are dynamic slip joints. It's dynamic because it is meant to move. When your cylinder expands just a little bit, we want it to be able to pull like a trombone. It moved a little. When it cools down, it can move back in. On these style systems, we want this during your detailed inspection. We mandate that you take off the exhaust system, you open it up, you inspect the cabin heat area. which by the way has less than 10% of the welded area that the normal exhaust does. And we want you to make sure you lubricate that with high temperature anti-seize, because that's its weakness. If you don't lubricate it, it will dry out, and now you might as well have welded it. Okay, Rube Goldberg runner-up, but that's how we did it on the Cardinal RG. The pictures are very low res, sorry about that, I don't know why that occurred. So how long do these take to install? Well, the initial installation is in the, call it 6 hours, unless you're a Cessna 182, Cessna 180, 182, 185. That gets a little more complicated because you have to make a new hole. Unless you're a 1957, or 56 or 57, you have an exhaust exit on the right-hand side, you need to have one on the left. So you have to cut a hole. We provide a template and all that. That's a tuned system. That's the leading edge design that we've brought back in, enhanced and brought back into production. These gases here run through this central chamber. This does have a flame tube, but I tell you, it is heavy, heavy duty. Typical expectancy on a muffler, okay, I'm speaking broadly, is somewhere around 1,000 to 1,500 hours of a traditional OEM design. You're nodding your head. You kind of agree with that number? Agreed, yeah. Okay. We got a guy in Hungary who decided that he finally was ready for a new one at 3,500 hours. Very overbuilt. So one of the things we decided when we brought it back into production was, if it ain't broke, we ain't fixing it. So it is still incredibly overbuilt, and we like it that way. So these gases come in here, go through that flame tube, exit over here. And then likewise on this side, what's in here is literally 2 sealed tubes. And funny quick story on that, we're the only customer for that tube size in North America. And boy, does the steel mill know it. So when we first bought it, it was 20 bucks a foot, and we had to buy what seemed like a lifetime supply. And then they started playing games with us, and they said, well, oh, you really want it? Yeah. How about 60 bucks a foot? I said, I don't like it 60 bucks a foot. They said, okay. So then when we went back to them, we got real serious because we were running out. And we said, okay, now we're really ready. They said, yeah, now it's 160 a foot. So I told our metal person, I said, well, I didn't get to screw you on the first call. It came through loud and clear on the second one, though. So we scrambled and decided and hummed and hawed, and we had to say, well, what do we want to do here? That's your cabin heat underneath that. I did not want to get into the welding business of welding, doing what everyone else does. You take a flat piece of metal and you roll it and you weld it. Because now you have a crack probability, right? And I'm trying to buy insurance for everybody. So we had to talk and beg, plead, and do whatever else we needed to do. And spoiler, we finally got them to come back down to 60 bucks a foot. That's what we just had to do. We had to suck it up and do it because we did not want to compromise on our design integrity of that. But this is the silliness that happens when you're the only customer for something like that. And so that's what we do. This is what it looks like on the side. There's that new hole cut out. We made some interesting improvements that weren't there before. For those people that are on floats or they have really giant 3-blade props, this cowling has to drop down 2.5 inches and move 2.5 inches to get around that, we call it the hook, okay? That's out that far for carbon monoxide avoidance. It also doesn't put stuff on your cow flaps, and it doesn't make you go on your belly. Well, if you can't drop it down and aft, we came out with a version of this that's 2 pieces. You literally just drop the cowling down straight, which is revolutionary for those of you that ever fought with a Cessna 185 exhaust where the thing is coming out at this weird angle with a hook on it, and you're trying to go around the big 3-blade prop and really have a good time. Now you undo the bolts and you go down. So those are the kinds of design innovations we try to do. That's the carb heat. All right, so why would you want a tuned exhaust system? Well, you want more performance out of the engine, but you don't want to go through that huge expense of getting a new engine. Maybe it's not even a possibility. Some aircraft, there is no STC version where you can go bigger. So you consider this. So there's an apparent gain. Oh, this is the great numbers. So that 160 horse engine I was talking about, we dynoed it. What we did was we took a 160 horse engine, we put the neutral stacks, the same things that Lycoming puts on, And we put it on there, and it did 159 horsepower. We put the stock exhaust on it, it did 133. Put on the tuned exhaust system, and it made 157. That is a 23.75 horsepower gain over the stock, but we did not go over the 159 or 160 number. That's what I was telling you about with where we essentially derated it slightly. We optimized it for the RPM that we all care about, not the one that is possible. So what is that? That gives you that extra performance by that scavenging. So the volumetric efficiency is improved, and technically your brake-specific fuel consumption goes down. It takes less gas to go the same RPM, same speed. That's cool. I mean, literally it's cool. Your cylinder heads will be cooler too. One thing that does happen, if we've taken the cylinder, the temperatures out of the cylinder, what do you think EGTs did? Did they go down or go up? We have one vote for up. Anyone want to vote down? Yeah, if you take the gases out of the cylinder and it lowers the CHT, does your EGT go up or down? Yeah, it goes up. It makes sense. The thermal energy doesn't just dissipate. It's got to go somewhere. So it went into the EGTs that go up. So it is normal to see a slightly elevated EGT. That's okay. EGT doesn't damage cylinders nearly as much as CHT. All right. I talk too much, you know, and I'm going to run out of time. So I'm just going to click through these things occasionally. Does anybody have any general questions you think would be useful for people? Yes, sir. How would you handle it with a turbocharged engine? Quite simply, we wouldn't. So the turbocharged engines, their exhausts are very fundamentally designed, and the turbocharged engines are usually, that's the only exhaust ever supplied by the engine manufacturers, usually, and they're all meant to work in harmony. It is possible you could tune an exhaust system for turbo entry, but the juice is not worth the squeeze. There's not a lot of room in there already. Sir?
On your straight pipe there, did that then meet the decibel level for the manufacturer?
Yeah, so all of our exhaust systems, we have to prove to the FAA that we are not any louder than the original OEM, and we do prove that.
Then the next question, have you thought about putting a stainless screen in there? Because if the screen blows a hole in it, it's not going to happen. What's the smile?
It is made of stainless.
I'm sorry?
It is made of stainless. Whatever's inside is stainless. Yes.
Any chance of putting a screen in there as opposed to the baffle? Because
I see.
it did lose part of the screen going through as opposed to the baffle.
Yes. Well, he's asking what if we put like a stainless screen in there, sort of like a capture system for the baffle. Some of our systems have that, some of them don't, and it really depends on the noise issues that we're dealing with. So, okay. If you want to ask more in-depth questions, I'll be here for a little bit after this. I'm the last guy, so until they kick me out, I'm here for a little bit. We're also going to be inside the Raven Hall tomorrow. If you want to come by, you can see the exhausts or take a look at it or ask questions, okay? Thank you very much.
Yeah.